Welcome to today's lesson on understanding the area under a velocity time graph. Our lesson plan is as follows. First, we'll see how the area under the velocity time graph represents the displacement of an object. Then we'll look at some worked examples of finding the area under a velocity time graph. So far, you have become familiar with velocity time graphs. You understand how these graphs plot an object's velocity against time, giving us insights into the motion of the object. Using this knowledge of velocity time graphs, we can now delve deeper to understand how the area under these graphs translates to the displacement of an object. This concept enhances our grasp of motion in physics, providing us with tools to quantify how far an object moves over time. Let's delve into a core concept, how the area under a velocity time graph can help us determine the displacement of an object. The area under a velocity time graph represents displacement, or how far an object has moved. When the graph is above the time axis, it indicates a positive velocity, which means the object is moving forward. The area under this part gives us the forward distance. When the graph is below the time axis, it suggests a negative velocity, meaning the object is moving in reverse. The area between the x-axis and the line gives the backward distance.
So even though we say displacement is the area under the velocity time graph, when the velocity is negative, we actually mean the area above the graph.
Yes, exactly. Displacement is always the area between the graph and the x-axis. When the velocity is positive, this is the area under the graph. But when the velocity is negative, this is the area above the graph. And remember, the other key point about the area under velocity time graphs is the larger the area under the curve, the greater the displacement of the object. Let's apply what we've learned to a few specific problems to consolidate our new knowledge. A car's velocity time graph shows us that from 0 to 4 seconds, the car accelerates from 0 to 6 meters per second. Then from 4 to 8 seconds, it travels at a constant velocity of 6 meters per second. Finally, from 8 to 10 seconds, it decelerates to 0 meters per second. Calculate the total displacement of the car. Pause the lesson here to have a go yourself before we go through the answer. First, we need to divide the graph into simpler shapes. The first triangle of the velocity time graph is from 0 to 4 seconds. The base of this triangle is 4 seconds and the height is 6 meters per second. Therefore, we can calculate the area using the formula for the area of a triangle, which is half times base times height. So we get an area of 12 meters. Now let's look at the second portion of the journey from 4 seconds to 8 seconds, which creates a rectangle shape. The width of this rectangle is 4 seconds and the height is 6 meters per second. We can therefore find the area by multiplying these two values together, which gives us an area of 24 meters. The final portion of the graph is from 8 seconds to 10 seconds, and we need to find the area of this triangle. The base of the triangle is 2 seconds and the height is 6 meters per second. So the area of the triangle is 1/2 times 2 times 6, which is 6 meters. Finally, we add these areas to find the total displacement. So the total displacement is 12 plus 24 plus 6, which equals 42 meters. Therefore, the car has traveled a total displacement of 42 meters. Now let's look at another problem. A cyclist's velocity time graph indicates that from 0 to 3 seconds, the cyclist accelerates uniformly from 0 to 9 meters per second. Then, from 3 to 6 seconds, they maintain this velocity of 9 meters per second. From 6 to 9 seconds, the cyclist decelerates uniformly to a velocity of 0 meters per second. Finally, from 9 to 12 seconds, the cyclist further decelerates uniformly to -2 meters per second. Given this velocity time graph, calculate the total displacement of the cyclist. Just like the previous question, we need to divide the graph into simpler shapes. Draw a first triangle from 0 to 3 seconds. The base of this triangle is 3 seconds and the height is 9 meters per second. The area is therefore 1/2 times 3 times 9, which equals 13.5 meters. From 3 to 6 seconds, we can draw a rectangle. This has a width of 3 seconds and a height of 9 meters per second. The area is therefore 3 times 9, which is 27 meters. From 6 to 9 seconds, we can draw another triangle. The base of this triangle is 3 seconds and the height of the triangle is 9 meters per second. Therefore, the area of the triangle is half times 3 times 9, which equals 13.5 meters. So the cyclist again travels 13.5 meters during this interval. Finally, we can draw a small triangle between 9 seconds and 12 seconds. The base of this triangle is 3 seconds and the height is negative 2 meters per second. We can calculate the area by doing half times 3 times minus 2, which equals minus 3. This number is negative because we have negative displacement, which we can see because we are below the x-axis. This means that the cyclist travels 3 meters back towards their starting point during this interval. We can now calculate positive and negative areas separately. The positive displacement is given by the total area above the time axis. So we get 13.5 plus 27 plus 13.5, which equals 54 meters. The negative displacement is given by the total area below the x-axis, which is minus 3 meters. Using these two totals, we can now calculate the total displacement, which equals the positive displacement plus the negative displacement. So we get a total of 54 minus 3, which is 51 meters. Therefore, the total displacement of the cyclist is 51 meters. Great work, that's the end of our lesson today. In today's lesson, we delved into the concept of how the area under a velocity time graph represents an object's displacement. We discussed how the graph's area above the time axis indicates positive displacement, while the area below suggests negative displacement. By mastering this concept, we now have a powerful tool to quantify how far an object travels over a period, enriching our understanding of motion in physics. Watch the rest of the GCSE physics course at Sophos Education.